All right, so what pressure is a force, which is pounds per square inch, okay? So, and that's a real important thing with pressure, in reading things. Is that, those lights up front, are they messing us up with the glare? They did? Yeah. That worked. All right, and we kind of went over this a little bit, that if people's weight don't change, if they put snowshoes on, they'll spread their weight out. And so they have less pressure because there's more area underneath their feet. So they don't create as much pressure, so they don't sink into the snow. So to calculate pressure, you take, it says pressure over area. I should have said force over area. Yeah, P meant pounds, so. I don't have that labeled properly, do I? Okay, so this should be force, not pressure. It should be force or weight or something like that. Okay. All right, and then we kind of derive this thing where 1 foot of water is 0.433 psi, 2 feet of water is 8.866 psi. And that it doesn't matter what shape you've got, as long as the water is continuously connected to a certain height, that will get you the pressure. And that's all there is to it. And that's right on your formula sheet there if you need it, okay? So you've got that available. It's just 0.433 psi per foot. And that's it. Anybody need the formula sheet? I had this thing on Friday, I think it was. Anybody else? All right, so this formula sheet's handy to have, of course, and this is what I'll give you when you take the test. Okay. Those things not moving?
No, I mean, yeah.
You're not in one of those classes, either something. So, why don't we show you? All right, let's one of the
No, what I got a question.
Yeah.
The pounds per square inch per foot, now is that square foot?
It's a linear foot. Okay. So every foot of water gets you 0.433 psi. And so you have to regardless of the shape of the tank, height and pressure.
That's because of gravity, right?
Yeah, right. It's just the weight of the water divided by the area. So yeah, you just take the height, whatever it is, in feet times 0.433, you'll get the psi. And it's no more complicated than that. Okay. So on this one page here in the book, you've got these many different examples, and the result on them is always the same, regardless of that shape. Even if you've got soil that's what we call saturated, filled with water, you get the same pressure caused by the water at the bottom. So none of these other things matter. It's just about the height. Okay, and then we went through a little practical example here of why they build these elevated tanks. They create a nice constant cushion of pressure on the system. So commonly what they'll do, they'll come in the morning a bit early, make the water that they need for the day, pump it when the power's cheap in the early morning. Because industrial users will get a break if they use their power during off hours. It costs less. So they'll pump it up into that tank and then just let that tank create a nice constant pressure in the system. Okay, so this water tank here would need a pumping station to create constant pressure, okay, because it's not elevated. So if you don't have hills, you build these kind of tall tanks is what you do. All right, now if you've got something other than water, and if you know the specific gravity, you would calculate the pressure due to water and then multiply that by the specific gravity to get the pressure. Okay, so 30 feet times 0.433 psi per foot, in this case times 0.92, would get you 11.95 psi. So the idea here is that this stuff, whatever this fluid is lighter than water, so it would create less pressure, essentially 92% as much pressure as water would. Okay. We good with that? All right. All right, now there's a few other things relating to pressure. Now where we got to then was we do have homework, so why don't we have a look at that? This is due on Wednesday, 6.1 through 6.5. So why don't we have a look at this? And if you got questions, you know, I'll take them. So there's 4 kind of straightforward ones. The 5th one's a little bit trickier. And you know, I won't do the 5th one for you, but if you got questions on it, I'll take them. So let's see here. All right, so do we got questions on number 1? Number 2? Anything on number 2? Everybody okay with that? Good. Do I hear anything for number 3?
Can you go number 3?
Okay, we can have a look. Let's see. Stupid thing turned off. Okay, number 3. What do we got here? We've got a tank. It has 283 pounds of a liquid. What's the specific gravity of the liquid? Okay, so on this one, what you're going to need to do first is find the density. Okay, and to do that, you got to find the volume. So the first thing to do on this is going to be to find the volume of that tank. Okay, so the tank is 1.4 times 2.4 times 1.2 for the volume. So the volume will just be the product of the 3 dimensions, because that thing is a, well, the simple word is a box, or a rectangular tank. Fancy word would be a rectangular prism. But whatever you want to call it, you get the volume by multiplying the 3 dimensions together. Okay, so 1.4 times 2.4 times 1.2, and that comes out to be 4.032 cubic feet. Okay. Now you're given that the amount, that the weight of this stuff is 283 pounds. So I'll do that next. So that's 283 pounds divided by the volume. Okay, and I'm just carrying the units through that because that's just going to tell me how to do this problem. See, I've got the pounds over the cubic feet. And when I run these numbers, what I'm going to get is pounds per cubic feet. Okay. And that's what I want for my density. And that comes out to be about 70.19. And the units are just right there. Pounds per cubic foot. So now I've got the density. So what I'm going to do next is compare this stuff to water, okay? So the density of this stuff is 7.19 pounds per cubic foot. The average density of water is 62.4 pounds per cubic foot. So I'll just divide the 70.19 into the standard of 62.4, and when I do that, I'll get a specific gravity of 1.12. And that's just going to be a number with no dimension on it, okay? That's just a ratio, so it doesn't have any units or anything like that on it. Okay? So that's the kind of step-by-step approach to that. So you need the volume, use the volume to find the density, then use the density to find the specific gravity. You're comparing it to water is what you're doing. And there's the specific gravity of water. So we got any questions on that? Okay, we're good? Alright. So we good on the one after? 6.4? Doing okay? Okay. Yeah.
So, I don't really have a problem working the fifth one, I just don't, I'm kind of blown away by it. I keep setting it up in different ways,
Uh-huh.
and I feel like the answer I'm getting isn't the answer that you're looking for.
Oh, okay. Well, we'll talk about that a little bit.
Okay.
And you know, early on, I give you one challenging one per set, just kind of for fun. I mean, don't get, you know, they're just to give you a challenge. Is what that's the intent of them. So, you know, kind of take it in that light. They aren't like make or break problems or anything like that. And honestly, I can't even figure them out. I just give them to you guys because I hope somebody out there could figure it out. Yeah, question.
On the last one at the bottom, is
Yeah.
it 58,500?
Well, this one I'm not going to give you the answer to, okay? Because this one. Oh, this one. Okay, now the answers are in Moodle, okay, when you need them. They're right in there. Let's have a look and see what the answer is. Well, you were referring to 6.5, right? Or were you referring to this one?
I think so, and she was talking about 5, yeah.
5,
Yeah.
okay. So, well, let's look at 4 and look at the answers. Now that 58,500, sure enough, okay? And most things I'll give you the answers if you look at Moodle, they're right there. Okay? So you can check yourself and make sure you're doing okay. All right. Okay, now I'll give you a hint on this last one here. All right, so the tank is full of water when it's 90 degrees, and then the temperature drops a lot down to 40. So find the height of the water in the tank. All right. Now let's kind of start off and just kind of look at it. Do you figure this height will be more or less than 20? Y'all good with that? It ought to be less? Okay. Because the temperature's dropping. Yeah. It's gonna get a little denser, and it's gonna.
So for real
Shrink.
practical, this is like when you buy gas at night, there's a bunch of gas in
It could be. Yeah, I never really thought about that, but yeah, I bet.
I
Yes.
mean, I was trying to relate it to something other than water.
Well, yeah, I think gas would act the same, and it might be more like pronounced, you know, bigger change. Yeah, I never thought about that. I guess night's the time to get it, isn't it? Yeah. Okay. Okay, now, is it gonna drop like down to 3 feet or something? No, it's not gonna do that, okay? So that's kind of, you know, first I just gotta look at, okay, what should my answer be? It should be a little bit less than 20, but not a lot, okay? So that's where my starting point on this. Okay, now, the hint on this is what changes with temperature? Why does this happen? The density changes with temperature, right? You all good with that? And what doesn't change? Yeah, see, you got a certain amount of water. That's not going to change. What it is what it is. I mean, there's a certain amount of water in there, and it's the density that changes.
So it's still gonna weigh 62.4
That's density there, okay? That will change. That number will change.
So the 62.4 is gonna change.
Yeah. There's a chart in chapter 1 that'll tell you how it changes. Okay? So that 62.4 is an average value. This is kind of the garden variety value we use, because most of the times this doesn't matter that much. I mean, it's just a little change here or there. It's not a big deal. But in this problem, you really got to look at that chart. Okay? It's in the book. It's in chapter 1, page 58, I think. Okay? Now, what doesn't change is how much the water weighs. There's a certain amount of water in there, and it's not leaving or doing anything. It's all in the tank. Okay?
So you wanna know how much the water shrank
Yeah.
from its temperature space?
Yeah. Right. Yeah. And relate that to the height, changing height of the tank. Okay? And there's many different ways to do this problem, as long as you set it up and clearly show your method, and throw some units in there so I can see what the heck you're doing. Okay? And just that's kind of about as far as I think I'd go with the explanation. But if there's any specific questions, I'd take them. But that's probably enough to get you going. Let's see. You okay with that? Okay. And get some people you work with, get some friends, work on it together, whatever. I mean, just figure it out. Okay. Now this is something that happens. I mean, in the winter, water's harder to pump. You'll spend more on pumping costs in the winter. It takes more energy to move the water around because of this change in density, around here. Well, yeah, now, yeah, ice is a whole different thing. But yeah, that's why I kept that above 32. If that went below 32, that would be a whole different thing. Okay. All right. So we all right with that? Okay. All right. So those are due Wednesday. And carry your units through that. I mean, one reason I like you to carry your units is that, I think it really does reduce errors. Another reason is, for your own self-interest, if your setup is nice and clean, and let's just say, you're doing a test or something and you get the wrong answer, I give partial credit, but I got to be able to follow what you're doing to do that. And sometimes I just get people just write down numbers, and if they're wrong, I just... I don't know where they came from, that's a problem. So it's you're in your own interest to show work and be systematic and all that, because then I can follow what you're doing. I go, oh, okay, one mistake right here. I'll just take a couple points off, So just show your work, okay? It's just a good habit. All right. So let's kind of get back into that chapter then, if we're good with the homework. All right, now there's different ways of measuring pressure. This is kind of, nowadays we use a lot of electronics, pressure transducers that read pressure and then convert it back into height and things like, or actually, yeah, they look at electric current and how it changes in different pressures. But in the old days, they used these things called piezometers. And I remember when I was in school, they were doing these experiments down in the hydraulics lab, and they had all these piezometers in a pipe, and they were running all these tests. And so a piezometer is kind of an old school way of measuring pressure. It's just a tube that goes into a pipe. And you just look at how high the fluid rises to in the tube, and then based on that, you can find the pressure, okay? So you just look at what this height is, and then you relate that to the pressure directly. Now, the problem here can be if you use water in the tube, water goes, it's only 1 foot only gets you 0.433 psi. So if you're measuring high pressures are just water, the thing, but you need a huge tall tube. So they've used things other than water, okay? Y'all know one of the big fluids they've used in here in manometers and piezometers? Yeah, it was mercury, yeah. Which, they don't use it anymore for obvious reasons. It's quite toxic, but I remember working, seeing those things, because, yeah, they do. Actually, I agree with you. If I want to measure a temperature, I'd want a mercury thermometer because they're just reliable and they're just straight up. These digital things are kind of all over the place. And I think it's the same with pressure, But there is that obvious couple of problems with them. One is the toxicity of mercury, and the other is they're not digital, they're analog, and you got to look at them and read them. So let's just have a look. So let's say we've got 14 feet in a piezometer, which would be a huge piezometer. I mean, that's like almost a story and a half high. But let's say we got that, and let's figure out what the pressure in the pipe would be. So what we've got here is a pipe that's essentially coming out of the page towards us. And what we want to figure out then is the pressure, okay, in this pipe. That's the idea. So essentially what we've got here is a pipe that does that and keeps going backwards, okay? Like so, and then we've got this piezometer sticking up there. So if that piezometer is 14 feet high, what do we got for the pressure? Yeah, that sounds about right. Okay. And the one thing I often think about these pressures is that people often make these too complicated. If they're having trouble with it, it's usually because they're trying to make it harder than it is. Okay. So that thing's 14 feet high. And how many PSI per foot? 433. And that's always on your formula sheet if you ever need it. And that comes out to be about 6.06 PSI. Okay. Now how about if we got some substance, which actually probably, well, there are some heavy oils, but let's say we got a specific gravity of 14.2. What would we be looking at for the pressure then? Yeah, it's up in the 20s, okay. And that's really about all there is with these piezometers, okay? You just take the height, multiply it by the pressure to height conversion there, okay? And that's really about all there is to it. And that's 25.5, was it? PSI. Right. Okay with that? Yeah. All right, now there's different kinds of pressure. We're looking at water pressure and fluid pressure here. But another kind of pressure that we deal with, that we deal with it so much that we don't even really think about it, is air pressure, okay? So let's look at that. This is called atmospheric pressure. And, when you watch the news report and they talk about atmospheric pressure, this is what they're talking about. And it's the same sort of thing as water pressure, it's just air is a lot lighter. If you're at sea level, like at Newport or somewhere like that, and you measure the column of air, a square inch in area, and if you go all the way up to the edge of the atmosphere, that air will weigh 14.7 pounds on average. So the atmospheric pressure is 14.7 psi-A, and I'll get to what that A is here in a minute, at sea level under average conditions. So if you look at this column of air, What's happening is gravity is pulling that in towards the center of the earth, and that has a weight of 14.7 pounds. If it's an inch, it has a square inch area for that too. Those are inches. They just kind of run together. The font didn't work. 1 square inch. IN instead of N. All right. So that's all that is. See, that's just the air going above your head, so to speak, up to the edge of the atmosphere. Weighs 14.7 pounds for every square inch you look at. Okay? And that's what causes the pressure. It's just like fluid. It's just the weight of the air. Okay? Now, the higher up you go, the less the air weighs, because you're going higher and higher, and there's less air above your head. So at sea level, it's 14.7. What's Bend? What's the elevation up there? 4,000? Okay, it's only 12.7 psi there. I lived in Flagstaff, Arizona. That was 7,000. That's 11.8. Yeah. Yeah, it does change certain aspects of water. Now, not all of them, because quite often this atmospheric pressure is on both sides, whatever you're working with, and it cancels out. That's the norm. But it affects boiling temperatures, and you actually water boils at a lower temperature when you're up high. And that's not always good if you're trying to cook something. So, yeah, right. So that's one thing that happens. It also affects how high you can lift water in a pump. If you've got like a static lift pump, like an irrigation pump that pulls water up and out of a river or something, you can't lift it as high at higher elevation. There's some things that it affects, but often it cancels out because it acts on both sides of whatever it is you're working on. No. No, I mean, there might be just a little bit of change in weight with height because you're further from the Earth's center and there's this equation that calculates gravity, but it wouldn't be, I don't even know if it'd be noticeable. But you also have the atmosphere pushing up on you too from underneath. It kind of balances out. So I don't think that's related to pressure. And if it were, it'd be so small. It's not something that you can. All right, so actually we use two different kinds of pressure. We use absolute pressure and gauge pressure. Absolute pressure includes atmospheric pressure, gauge pressure does not. Okay? Now, gauge pressure is the normal pressure we are familiar with that we work with every day. If you go to your car and measure the pressure in your tire, that's gauge pressure because you're using a gauge. Anytime you're using a gauge, it's gauge pressure. And anytime we talk about a normal everyday pressure, it's gauge. But there's times when we need to use what's called absolute. It doesn't come up a whole lot, but it does a bit. So there's a relationship between these things. And it's on page 66, and it's on your formula sheet too. So the absolute pressure is the gauge pressure plus the atmospheric pressure. So gauge does not include atmospheric pressure. Absolute pressure does. That's the idea. Well, let's look. I'll show you an example of why gauges just don't. They just discount it because quite often atmospheric pressure is working again on both sides of the gauge, and so it just cancels out. 99% of the time it cancels out. Every now and again, though, we have to consider it. And vacuums. When we're dealing with vacuums, we got to deal with it. So let's look at pumping up a tire. If you want to pump up a tire to 30 psi of useful pressure, you got to pump in 30 psi more than atmospheric pressure is what you got to do. Okay? So what you've got pushing on your tire, and pressure acts all different directions. Think of like a bunch of marbles. If you push down on the marbles, they'll kick out also. Pressure's the same way. okay? So if you've got this tire, atmospheric pressure pushes from all different directions on the tire, is what it does, okay? So if you want to pump that thing and get 30 psi of useful pressure, you've actually got to put 44.7 psi in the tire. You got to counteract that 14.7 of atmosphere pushing in on it. Okay. Now, if you put a tire gauge on that, the tire gauge is going to read 30 psi because the difference between the 44.7 and the 14.7 is 30. Okay. Okay, because what's going on here is you've got 44.7 pushing on that side of the gauge, but on the other side of the gauge, you've got the atmospheric pressure pushing, and that's 14.7. So your gauge is just going to kick out 30. Okay? That's the useful pressure that you've got, the pressure difference. So in everyday situations, you don't usually worry about atmospheric pressure. It's just something we're used to, and it works usually on both sides of the things we're working with. So it just cancels out. Okay? It's not a big deal. So if you're under 20 feet of water, what's the absolute pressure you're dealing with? Uh, 3.3. Yeah, that's right. Yeah. Yeah, what you do, you take 20 feet, and the gauge pressure, you just take 0.433 psi per foot, and that would get you 8.66. And then you've got the absolute pressure is the gauge pressure plus the atmospheric pressure. So that would be 8.66 plus 14.7, and that comes out to be what, 23.36? Yeah, call it 4, whatever. So you call that PSIG, okay? And you could call this PSIA, is another way to do it, for absolute. Now, this may not be a number we need to know because, you know, unless we've got a vacuum that we're dealing with, we also have the atmospheric pressure pushing on the other side of whatever we're looking at here, a dam or, you know, whatever we've got under 20 feet of water. So usually it doesn't matter that much. Okay? But there's one special case where it does, and that's when you got a vacuum. Because when you have a vacuum, you're lacking pressure. You've pumped some of the air out or all of it out. So now there's no longer any atmospheric pressure when you've got a vacuum. So absolute pressure is used when we describe a vacuum.
Think of like the vacuum for like a metal cylinder.
Sure. Yeah, I could.
That would,
Well, if the metal cylinder was like a submarine and you'd had the hatches open, then you took it down under the water, you got atmospheric pressure in there already, okay? So it could be like a cylinder that you've pumped the air out of. It's anything. And really, the reason we're going through this, it's not that common of an occurrence, but it is an occurrence at a pump. When you got a centrifugal pump, if you guys you've had pumps already, right? A little bit, okay. You all know about centrifugal pumps. The impeller spins, it throws whatever's in the volute out, and that leaves a vacuum behind. And that's why you can lift water into a pump. Okay, so a vacuum is a pressure that's below atmospheric pressure. A vacuum occurs when you remove the atmosphere from an area. When you use a straw, that's what you're doing. You're pulling the air out of the straw, leaves a vacuum behind, and you can push water up into the straw. Same thing with pumping, irrigation pumping. Okay. A vacuum has a negative gauge pressure, which is a little awkward to work with. So if you've got 3 psi of vacuum, that would be negative 3 psi G for gauge, because it's 3 psi below atmospheric. Okay? So a gauge would go to negative 3, because a gauge zeroes out at atmospheric pressure. You just take a tire gauge and just lay it on the driveway, it reads 0, unless you've done something to it. So if your vacuum has a negative gauge pressure, you're below atmospheric pressure. Okay? So that would be a negative gauge pressure. But when you do the little formula here, if you look at the absolute pressure, you would take the gauge pressure plus the atmospheric. See? So the gauge pressure is negative 3, the atmospheric pressure is 14.7, so that's 11.7 psi absolute. Okay. So minus 3 psi gauge is equal to 11.7 psi absolute. All right with that? There's 2 different ways of measuring the same thing. They both use psi, they just got different 0 points. Gauge zeroes out at atmospheric pressure. Absolute pressure zeroes out for no pressure whatsoever, total vacuum, like in outer space or something like that. So an absolute vacuum is the complete lack of pressure. Absolute vacuum is 0 psia, which is negative 14.7 gauge. Okay. All right, we head back into the past, and we got all these smart people in Europe figuring things out in the Renaissance and all that. And so they start to realize there is something called atmospheric pressure, and they want to measure it. Okay? I'm not quite sure how they went about this, but here's one way to do it. You ever seen those self-watering dog dishes? You take a 2-liter bottle, fill it with water, flip it, and get it in a pool of water, and it won't just all drain out. Really. You know what I mean there? Dog dishes. Okay, and that's actually because of atmospheric pressure, and that's similar to a device that can be used to measure atmospheric pressure. Let's see. Let's have a look here. Kind of thinking, I remember when those things came out, they were 2-liter bottle flipped upside down into a dish. Now they probably got electrical transducers and soothing music for the dog and things that read your dog's pulse rate and all that. That's probably the current version of these things, but let's see. What would I call this? Automatic dog water dish or something? Self-filling? Self-filling? What? Livestock? Oh, okay. Oh, they do? Okay. Water bottle? Okay. We're good. I'm always so nervous when I go into Google Images. I just never know. There we go. Okay, that one's only 2193. There we go. It's just like a water tank. There we go. Yeah, that's. Oh, okay. There we go. I think we're good. Okay, so you just get it. That looks like a water cooler there and stuff. You just get this bottle, you flip it upside down, and it just slowly fills into the tank. As long as there's water down below, then the tank goes in. Let's just get a quick look at what's happening there. Watch the video. You got a video? Come on, yeah. Video. I don't know. Yeah. Gee, yeah, I'm sure it's good. Being on the internet requires a certain amount of discipline, right? Or you can't watch certain things you just don't want to go there. But anyway, here we go. So what do we got? We got 3 minutes. We'll do the quick version of this. We'll come back to this on Wednesday. But let's have a look. So fill a tube with water, turn it over, and place it in a pool of water. So let's see what's happening here. Okay, what's going to happen initially is your column of water is going to drop a little bit. And when it drops, see, it's sealed any air from getting in there. You've got a vacuum up above. So there's going to be a little bit of an air, and it's not an airspace, it's a nothing space. It's a vacuum. There's nothing up in there. Now what you're going to have is atmospheric pressure pushing on the other side, and being as that works in a fluid like marbles, that'll push up into the tube, is what it'll do. All right. So the water in the tube will drop, and there'll be a vacuum at the top. Atmospheric pressure will hold up a column of water. Okay. Now the average atmospheric pressure is 14.7 psi. So what that'll do, if this tube is a square inch of area, that'll hold up 14.7 pounds of water, if that tube has an area of a square inch. Okay. So we're going to hold up in this 1 inch area tube of water, dig around 14.7 pounds of water, so we can figure out how high that is. And that's on page 69 there. So we've got a volume of 1/12 of a foot by 1/12 of a foot, because that's an inch by an inch, times whatever the height is. Okay, and that's going to equal 0.006944 H cubic feet. Okay, the weight will be the specific weight, which is the density, times that volume. So we know we're holding up 14.7 pounds. We know that water weighs 62.4 pounds per cubic foot, a little typo there, times 0.006944 cubic feet. Solve for the height, it's 34 feet. Okay. So atmospheric pressure will hold up a column of water 34 feet high. It's 3.5 stories high, okay? And that is dependent on having a perfect vacuum up there, because there's nothing pushing back. Okay. All right. Class is over. All right. There we go. So, all right. So the homework's due Wednesday. We'll finish this up on Wednesday too, right?